this video, we will be talking about scientific notation and significant figures, as I promised. So, we'll be answering problems, and I'll be demonstrating the policies that you have to know in order to determine how many significant figures are there in, say, a whole number or a decimal number. So, there is a strategy that our teacher has taught us. If it's a decimal, if there's a decimal present, you read to the right. If there is no decimal present, you read to the left. Just like what I've shown in numbers 1 and 2. So, in number 1, we have 97.200 liters. Uh, if you want to determine the number of significant figures, reading to the right, we have, of course, all numbers that are not zero, they're all significant. And if you have uh, a given with a decimal point, you count everything when there is a non-zero number. Starting with a non-zero number. So um, at the start, we already have a non-zero number, which is 9. So we count all the way. So 1, 2, 3, 4, 5. We have 5 significant figures in the first number. For number 2, we read from the left. I mean, to the left.
Latte.
So yes, had it not been for the 6 here, then these 3 zeros would not be significant. So in total, we have 4 significant figures for number 7. Number 8, we count to the right. 1, 2, 3, 4. So again, zeros sandwiched between integers that are not 0 are significant. And whatever is at the right side, if there is already a non-zero number, say 3 and 6, or any of those two, then the 0 after it is already significant. That's the policy for the ones with decimal points. So here we have 4 significant figures. Number 9, 2.845. All of these numbers are significant. There's no 0 at all, so yeah, for SF. How about number 10, 8,000. So disregard all those zeros. These are all not significant. So we only have one significant figure for number 10. That is the policy for numbers without a decimal point, in which case we read to the left, from the right to the left. We count any number that is significant if it is a non-zero integer. In this case, it's number 8. So yeah, round off the. Alright, we have a new set of questions. Round off following measurements to 2 significant figures. So we already know how to determine the number of significant figures. This time we will be rounding off given numbers. So let's start with number 1, 0.09023. The technique is, let's say particularly for number 1, we have a decimal point. We will move the decimal point to whatever number is closest to it that is non-zero, in which case it's number 9. So let's recopy the entire thing. 0.09023 12 9.023. We don't have to copy it anymore, since if you round this off, 2 isn't big enough, so we'll just write 0 anyways. I think we all know that policy now. And what else do we have to understand? We put the times 10. Since we moved the decimal point twice to the right, so 1, 2 times, going to the right means a negative exponent. On the contrary, if we go to the left, then that's going to be a positive exponent. And then don't forget to write the unit, which is kilometers. You'll get a very big deduction if you don't write the unit or if you forget it. So yeah, being careless is gonna take a toll on your grades. So 9.0 times 10 raised to negative 2. That's correct. Let's go with number 2. 12,831 millimeters. 2 significant figures. Alright. Let's copy the number again. The decimal point will always be there, naturally, and by standard. 1, 2, 3, 4. And since 8 is greater than 5, the 2 before it will be 3, so 1.3. And then times 10. How many times did we move the decimal point? 1, 2, 3, 4. So that's to the left, so our exponent will be positive 4, or just 4. And then copy the unit. This is the final answer. 1.3 times 10 raised to 4. Let's see. Yeah. 39.9 grams. Wait, you might ask why. Uh, uh, you might ask the reason why I moved the decimal point between 1 and 2 and earlier between 9 and 0. Uh, that's always going to be the rule. Uh, Let me show you the same kind of rule that you're supposed to do for number 3. You move the decimal point to the left in between 3 and 9. So that makes but before that though, 39.9, round that off, that becomes 40. So if you round that off, we get 4.0. And because we moved the decimal point one time to the left, we get an exponent of 1. And then grams. Yeah, that's exactly the same. Let's go to number 4. Alright, 674.212121. Move the decimal point 2 times to the left. 1, 2. 6.7. It's not 6.8 since 4 is less than 5. So 6.7 times 10. We move the decimal point 2 times to the left, so that's positive 2 as an exponent. Then just copy the unit. So 7.056 milligrams. Make it 7.1 since 5 is, well, it's equal to 5 as a standard, but then yeah, that makes us convinced that we have to round off. Instead of 7.0, we write 7.1 and then times 10 raised to 0. We didn't move the decimal point anywhere, it stayed to where it was. So yeah, that doesn't make any difference. Any number that is raised to 0 will yield an answer of 0. An answer of 1, which doesn't make any change with 7.1. 7.1 times 1, it's still the same, 7.1. Let's try number 6. 30.1. Let's try that. 30.1. Wouldn't mean much though. So 30.07. Move the decimal point 1 time to the left. So 3.0 times 10. Since we moved the decimal point 1 time to the left, it's raised to 1. And then write liters as the unit. Number 7. We move the decimal point 1 time to the right. Actually, let me round off first. 2.29 hours. And then 2.9. We moved 1 time to the right. 2.9 times 10 raised to negative 1 hours. Let's see number 7. 2.9 times 10 raised to negative 1. Okay. Number 8. How many numbers do we have left? Oh, we still got a lot. Alright, 7,956. That's going to be 80.0. 8.0 times 10 raised to 1 seconds. We move the decimal point to the left, so that makes an exponent of positive 1. Let's see again if our answer is close. Yes, it is. I almost forgot though. We were supposed to, the decimal point was here. So 1, 2, 3 zeros to the left.